Section 2.4, one-sided limits and asymptotes. Now we have talked about limits, but now we're going to talk about limits that you approach only one side. Normally we approach a limit from both sides, but once in a while we might want to approach it from one side only. An example would be, say if you have the square root of x, as x approaches 0. Well, you're not going to approach from the negative side because it's not defined, so you're forced to approach only from the positive side. And of course, at the square root of x, the limit is just 0 when x approaches 0. Now, there's a good reason to do that, but sometimes we just want to approach from one side for no apparent cause. That's just how the function is defined, or that's all we care about. In any case, when we approach one-sided limits, there's sometimes we have to consider a case where the function f is not reaching any value because it's climbing up higher and higher to infinity, or dropping lower and lower to negative infinity. In that case, we call it the function of f as x approaches, well, from one side. The plus means from the positive side, then minus means from the negative side. But anyway, so if x approaches the value, say a, if the limit is approaching infinity, that means the function f is getting very, very big, and it doesn't stop getting big, it just climbs up there forever. Now, we can use a similar definition as delta epsilon definition for this kind of limit. And remember, this kind of limit is different from the regular kind, where the limit actually reaches a number, because infinity is not a number. Okay, the infinity is only a direction, means we will go without stopping. Any number is where you stopped, even if it's a billion or a trillion. Infinity doesn't stop. So we have this definition, we have a similar definition which states that given a large number n bigger than 0, I don't care how large it is, a huge number, there exists a delta such that as long as x is within delta of a, in this case since we're approaching positive, x is bigger than a, okay, in that tiny little neighborhood, as long as it's small enough, every value of f is going to be bigger than that number that you gave. That's huge. Remember, x is not equal to a. That's why it's bigger than 0. X cannot, because we don't care what f is actually at a. Usually it's not defined, which is why we care about it. But that f is heading towards the endless infinity in certain cases, while as x approaches a, and therefore the definition goes like this, so that we understand that f is going to be bigger than any number we can think of. Now, an example of that, of course, the most obvious, easiest example to think of is let f of x equal to 1 over x. The graph of that looks something like this, and you have this thing, okay, as x approaches 0, from the positive side it crawls up positive, and then if you approach from the negative side, it crawls down negative. So it has two limits at x equal to 0. It's not defined as 0, but if you approach from the positive side, the answer is the limit of f is positive infinity. And then if you approach from the negative side, the limit is negative infinity. Now, the vertical line here, where the lines are crawling closer and closer to its crop, but never reaches it, those are called asymptotes. It's just a semi-interesting name. The asymptotes are normally found in several situations. Well, actually, in most situations, is when you have some kind of a rational function, and then the denominator is going to 0. So somebody's going to, the function is forced to climb up or down, either way. And then, so to find the asymptotes, you always figure out the points where the denominator is 0, and those are your asymptotes. So in this case, of course, it's just x equal to 0. The line, vertical line, x equal to 0 is your asymptotes. Now we can do a simple example here. Let's say we have a function f of x equal to secant squared x. That is one of our examples. And then we want the limit as x. So we want to know the limit as x approaches, well, pi over 2, of course, because that's where the cosine becomes 0. So what is this thing? Well, as cosine, we know the function, the graph of cosine. the cosine function goes something like that. This is from 0 to pi, okay? And then, of course, then that means the secant function, which is 1 over, is going to look something like this. This is pi over 2. And along this line, because along this line, this thing is going to curl up like this. And it's going to, and then over here is going to do the same things in the mirror image symmetry. So then pi over 2 is going to be your asymptote. So the asymptote x is x equal to pi over 2. And then the limit as f, the limit as f going to x goes to pi over 2 from either side, from plus or minus side, okay, fx is going to be positive infinity. But because they both cross, again, remember that the infinity is not a number. So you cannot say things like infinity equals to infinity. It's just a direction. So this just means both in crawling from both sides of f, function f is going to rise indefinitely.